This is joint work with Hamza and Omar Fawzi. And I'll start with introducing a bit the problem we're looking at, the free energy problem in one dimension. So think of a spin system with some, for example, electrons on a lattice in 1D. Each has a spin. And so each has, if you want it more mathematical, a local Hilbert space of d dimensions. And the whole system then has a d to the n dimensional Hilbert space. To use the fact that it's one-dimensional, we put a Hamiltonian, and we make it a nearest neighbor Hamiltonian, so always just interacting between two neighboring spins, just as in the tutorial about Hamiltonian simulation. And as its translation variant, we only specify a single matrix here. So the whole problem input is just in this one matrix, a d squared times d squared matrix. Then to build up actually the Hamiltonian of the full system, we just put these two local terms on all pairs of neighboring sides, so here and here and here, and sum over them and get our sparse but large d to the n times d to the n matrix, which is our Hamiltonian. The problem you're looking at is the free energy. It has this formula, which is basically you take this matrix I just introduced, the Hamiltonian, and then it's exponential. As opposed to the Hamiltonian, this is no longer sparse. So just computing this for a certain n is like an exponentially large matrix in n. So if you want to compute this and you do the naive thing, just take a reasonably large n for this limit and just compute that, then you will have an exponential runtime in n. So our goal is to get beyond that. Here T is the temperature, which is, we usually use the inverse temperature 1 over beta. And then we normalize the quantity by the system size so we can take a limit. So it's actually the free energy density more precisely, but I will not really say that. Also this quantity, the trace of this exponential is called the partition function. This is a rather maybe abstract quantity, but it's quite relevant to us. For example, the thermal state, which I define here, it's not going to be particularly relevant for the talk, but I just give it here, which is just this exponential divided by a normalization constant. Encodes the information about the thermal state, and so you get these thermal expectation values either by the thermal state, but you can also write them as derivatives of the free energy. So basically everything you might want to know about your thermal system is encoded in just this one function, which is why we just like restrict ourselves. How can we compute this function? Everything else, energy, magnetization, heat capacity, basically just follows. And another motivation to look at it is, in general, if there are phase transitions in your system, you will find them by looking at your free energy and checking it for non-analyticities. This is basically just the motivation. We really now restrict ourselves to computing this single quantity. Also, an alternative formula for it is given by this expression, which is some minimization problem. Again, we first take some finite system size and minimize over all possible quantum states the energy minus temperature times entropy. So it gives you a more physical side, which says like at low temperatures this is close to the ground state energy. At high temperature it will give you something with it maximizes the entropy, so something close to the maximally mixed state. Also, why I show this formula is you directly see if you consider the free energy as a function of temperature, you see that one limit where this entropy term vanishes is the ground state energy. And it's known that computing the ground state energy, even in this setting of translation variant, one-dimensional systems, is QMA hard. So whatever algorithm we come up with for computing the free energy, it can work at every finite temperature, and it will actually work at every finite temperature. That was also known before. So every single point here can be computed in polynomial time. But on the other hand, the scaling of the runtime has to be bad with temperature. So the closer you get, the harder it has to be. And in fact, computing this single point here is QMA hard. So we can then do some sort of reduction really by just what you see in this graph. Take a small temperature to approximate the ground state energy. This tells you a polynomial runtime, and beta should not be expected unless some complexity theoretic assumption is violated. So with this like introduction, let me start with our result. What we give is an algorithm for the free energy. And I give you here, I want to make a point that the input of our algorithm is just a thing that does not scale with system size, because we take a limit, there is no system size. So how do we actually describe something like complexity or runtime? The only relevant parameter with which you can actually consider runtime is a precision. So we take two inputs. One is this matrix here, which is the interaction term, and then what accuracy do we want? So the question is, how does the runtime of our algorithm scale with the accuracy that we want? And the output is then an estimate for the free energy. So as we have already seen from the title, our runtime is subpolynomial. So basically, you have an exponential of log 1 over epsilon, that would be polynomial, but we divide by an extra term log 1 over epsilon. So whatever polynomial you take, this is actually also the previously best runtime, a polynomial in 1 over epsilon, we are better than any possible constant coefficient here by a tiny bit. As I said, we don't expect this to be good at any temperature, so we say this holds if you fix the temperature beforehand. And we also fix the norm of this Hamiltonian term. Otherwise, you could just include the temperature dependence in the Hamiltonian term. And then for the fixed temperature, we can do this. Actually, if you would write down the whole runtime, including the temperature, it would be doubly exponential. That's worse than our converse result, but we wouldn't expect it to be too good. Besides the theoretical side, we also actually can say that one can actually do is, it's quite a simple algorithm, it takes just a few lines of code. And it also gives you not only the free energy just by the way we constructed this algorithm, you will just get the thermal state as a side result of your computation quite easily. So it's maybe, I mentioned beforehand, you can use the free energy to compute everything, but you actually get a more convenient representation of the thermal state straight away. When I say it's easy, simple to implement, then why shouldn't we do it? And we did it, and it's actually, compared to what I just said about doubly exponential dependence in beta, we made the observation that it's not as bad. We have here some results. This parameter L that comes up everywhere is basically something that describes the runtime. So these curves describe running the algorithm at different runtimes, and none of these curves took particularly long, it all took a few seconds. And we compared the result of the algorithm with an analytic solution for this XY Hamiltonian, which is just well known. There's some old work with beta ansatz that gives you the true result of the computation. And actually up to some reasonably medium-large temperatures, you actually get really good error rates, so you can actually use this algorithm. I will give some intuition for the proof by starting with the classical case, which is actually like just completely solved problem. And some of these techniques will carry over to the quantum case, but some will not. So I'll just start by introducing the classical case and restricting our problem to this Hamiltonian, which is diagonal. Means like, I must be careful. Before I had these indices describing the sites on which the Hamiltonian acts. These are just numbers, real numbers. And each of them gives you the energy of any configuration of neighboring sites. So if you have the first site in the first state of the spin, and the second one as well, you have this energy and so on over the whole diagonal. That's a classical case with a diagonal Hamiltonian. And the rest of this matrix is just 0. So writing down this trace of the exponential of the Hamiltonian looks like this. You just have the trace, just the sum over all configurations. And then you have this exponential, and you don't have matrices up there anymore, but you have just real numbers. That's quite convenient because you can just take this Hamiltonian apart. This is a well-known trick, which you will find in any statistical physics textbook. Unfortunately, each of these terms just depends on 2 of the indices over which we are summing. So you can actually do it one by one, and each of them just looks like a matrix multiplication. So if you introduce a matrix and write down the entries of these numbers in a matrix, then you see this whole formula is just a matrix multiplication. And you write it down, or many matrix multiplications, so you write it down as an exponential of a matrix. Then we are interested in the logarithm of this quantity normalized. And the only thing that will actually contribute if you take the limit n to infinity is the spectral radius of this matrix. So you get this neat closed formula for the free energy. This log partition function up to the temperature, this is the free energy, can just be computed by the spectral radius of the matrix, of this transfer matrix T. Even better, you might now envision some nasty, degenerate eigenvalues, imaginary eigenvalues. Fortunately, this matrix has clearly just positive entries, and that's why we can use something called Perron-Frobenius theory, some very old linear algebra result, which tells us the eigenvalues, the largest eigenvalue in absolute value will be real and it will be unique. And you can just compute this as an eigenvalue problem then. So this is now the formula of the largest eigenvalue together with this normalization by the temperature. And also, if you want the thermal state, you just look at the corresponding eigenvector here, and it will give you the probability distribution of this thermal system on one side. So these are the probabilities of being in the states of the system. And if you want probability distributions of several sides, you can construct this all in this transfer matrix. I'm not going into detail there, but everything is basically just one linear algebra computation, and then you have solved your problem. Also including the ground state problem, which I think you can even do a little bit easier by just some combinatorial consideration, but also you can take the limit here and get the ground state. So everything in the classical case is quite clean and easy. The bad news, still one more thing is, what the intuition behind this is classical thermal states have a Markov property. So classical, this is in any dimension, classical systems in a Gibbs state are Markov networks. It means, in particular in 1D, if you know which state one of your spins is, and you want to give the probability distribution over some region A, this does not depend any longer on the region C as long as you know what B does. This is like this conditional independence, which is equivalent to this Markov network structure. The quantum case is less favorable. We have no longer this Markov property. We have something like an approximate Markov property, which gives us an intuition. Maybe something similar works, but it's not really the method we use. It's just like an intuition that we have. And also, as I just said, the classical case has this easy ground state problem as well. We already know in the quantum case, the ground state problem is hard. So probably the whole problem should be at least slightly more sophisticated. But still, we try to do something similar. And there has been something introduced analogous to this transfer matrix, a so-called non-commutative transfer matrix. This is a much larger formula than the one I showed before, but it has some analogy with the classical case. It's something that acts on operators and maps them onto operators. And it has this exponentials of Hamiltonian a bit, as we saw before, but not just one of these two-side interaction matrices, but a sum over like L sides, and then a Hamiltonian L sides. You divide it by 2, not important here. And then one which goes from 2 to L sides, and one which goes from 1 to L sides with a minus sign. So you can see again, if you have a commuting Hamiltonian, then you basically have the same terms here as here, up to one extra term here, and it's basically cancelled, and it's actually, the formatting is a bit different, but it's basically the same thing in the commuting case as this classical transfer matrix. So this is kind of an analogy, and also it has already been proven by Araki, who introduced this map, that you can take a limit of this map. This is then something that acts on infinite dimensional operator algebras, and that the limit of this map will have the thermal state as an eigenvector, and the free energy, again up to some logarithms and stuff, as an eigenvalue. This is just defined in this functional analysis sense. So we want algorithms, so we are not happy with just the limit of this map. We want actually something finite dimensional which you can work with. Yeah. So, okay, the obvious candidate of something finite dimensional is just the map itself. Fix this L here, and look at this map. And basically the technical problem we're working on is, does the eigenvector and eigenvalue of this map converge? And how fast? You already know what the limit is. It's the right thing that we're looking for. The tool that we use, that has already been used in the previous work from Araki, is this term here, which I've beforehand told you. In the commuting case, this is a very simple thing. In the non-commuting case, this is not just something that depends on the 1-2 term, but something that like spreads over out to several sides, but it's like approximately local and does converge super exponentially fast. The super here is important because that is what our algorithm, what makes our algorithm a little bit better than previous ones. There are some technical problems here. This map is not Hermitian. On the other hand, it's positive, so you cannot use some standard perturbation theory. I'm dropping some words if you know them. Otherwise, this is a bit technical here, maybe. You have to find a candidate of a possible eigenvector or something close to eigenvector of the map. And a bit intuitively, we use the thermal state as something close to the eigenvector. And then need some variational expression and operator inequalities to prove some convergence of the eigenvalue. As I said, the super exponential is important here. It carries on. With these techniques, we get that the eigenvalue of these LL maps converges super exponentially fast in L to the eigenvalue of the limit map, which is this infinite dimensional object we want to avoid. Then, as I already mentioned, we are interested in the free energy mostly as a proxy for other quantities. In particular, the thermal state is usually a quite convenient representation of everything you might want to know about your thermal systems. And as I said, you can just take this algorithm as a black box thing, vary some parameters in your Hamiltonian, get some derivatives, and just use this algorithm that I just presented for the eigenvalue, and get every thermal expectation values you might want. But you can also just look at the eigenvector of this map. It's kind of intuitive that if the eigenvalue already converges, then the eigenvector might also converge. It's technically another slight difficulty, namely that we have to confirm that this maps that are presented here is not just, it's obviously a positive map, because you can see that it's this sort of sandwich thing, which will always map positive operators onto positive operators. What we need in addition is that it's has a permittivity condition, that it also maps any positive semi-definite operators to positive definite operators. And we need some like lower bound, how small can the smallest eigenvalue be. That's also basically then all done with the techniques from this old paper from Araki, and some Perron-Frobenius theory for positive operators. Something like the Hilbert's projective metric comes up here, but yeah, that's just some names if you want to look it up. With this, I'm about to wrap up. Just a short overview of what we did in our work. We present an algorithm for the computation of the free energy in translation invariant 1D quantum systems. So this is all the conditions that we have. The proof techniques, interestingly, come all from some works that actually originally looked at analyticity of free energy, or you might also know it as non-existence of phase transitions in 1D. All these things have been proved with the techniques that we now use to look at algorithms. And also, as I mentioned before, you can actually just use it. So if you do numerics, then I recommend. One thing I find neat about this thing is, when I talk about analyticity of free energy and mention phase transitions, then it's quite interesting to look at where do we have phase transitions and where do we have efficient algorithms. It's basically the same thing. In one dimension, there's this folklore thing, there are no phase transitions in one dimension. This is at least true for thermal phase transitions. So everywhere, at any temperature that is above 0, there will be no phase transition. And for all this regime, we know that there are efficient algorithms. Ours is not the first one. There was previous work by Kuwahara and Saito that proved the polynomial-time algorithm. Ours is now subpolynomial. But in particular, we use actually the techniques that relate to phase transitions to also prove algorithms, which fits quite nicely in this picture, I would say. On the other hand, as soon as you go to the ground state, at least in quantum case, you will have a QMA hard problem, already in 1D translation invariant systems. On the other hand, as soon as you increase the dimension, the problem becomes computationally hard. If the temperature is too low, that is actually a result already about classical systems. And that's also where you know that there are phase transitions, both in classical and quantum systems. And converse to that, as soon as you get rid of phase transitions, you also get to efficient algorithms which have polynomial runtime in this inverse error. There's also nice work by Haro, Meraban, Soleimanifa, where they basically really relate these two things directly together. With this, I'm at the end of my talk, and thank you for your attention.
Nice talk. Any questions? Yes.
Thanks for the nice talk. So for the super exponential decay, I'm wondering if you mean something like L to the factorial, which is slightly faster than like exponential?
Yes, it's basically an exponentially growing function divided by factorial, yeah.
Sure. So then can you expand a bit on why this factorial thing is important, like why exponential alone is not sufficient?
I mean, it's just that we get this as a result. Like we can use a subpolynomial time algorithm because basically you have the algorithm is really just takes this map, fix the L, and computes the spectral radius, and this map grows. The size of this map grows exponentially with L. So if you pick an L, you get like a runtime exponential in L, but error super exponentially small in L. And this, if you can just basically reverse compute the L that you need for any error, and then you get to subpolynomial time.
Thank you.
Thanks for your talk. I was just wondering, is the fact that you can compute these free energies at fixed temperature for one-dimensional systems efficiently, but not for high-dimensional systems, is this related to the fact that these one-dimensional systems are beta ansatz solvable?
I think the beta ansatz is for specific one-dimensional systems. There are also, I mean, this is the integrable case, but not every 1D system is also integrable, and this works generally for any spin systems. And doesn't rely on one of these particular ansatzes.
Okay, thanks.
So thanks for the very nice talk. Your argument, so it was based on this proof of analyticity in 1D, and I was curious whether sort of in your last slide, essentially, there you say like in higher dimensions you can compute it above some threshold, but could you also efficiently compute it if you somehow know that you're in a region where there's no phase transition, so the free energy, you know the free energy is analytic in this region? Would that be sort of enough to have efficient algorithms, do you think? Is that known?
Yes, actually that was written in this paper. That you can, basically it's about cluster expansion, Taylor expansions of your free energy, and it really relates the error you make in cutting off this Taylor expansion to the poles in the complex plane of the partition function. And they really relate this, as soon as you're away from these poles, you can compute the free energy efficiently.
Thanks for the talk. So I just wanted to clarify one point. So this Gottesman-Irani paper that talks about QMA-X hardness, so my understanding is that that's for a finite n, and n is the input. Whereas in your problem, you said that you wanted the entries of the matrix to be the input, and then you directly take the limit of n going to infinity. So do you have evidence of hardness in that regime, or am I misunderstanding?
I'm sorry. So this paper, I think this paper, Gottesman-Irani, actually, the first system was like this guitar of clock constructions on like finite size, and then they put it to one dimension and reduced the locality. But this paper actually really shows you can just encode it in a two local Hamiltonian translation variant, just this one input matrix, and basically encode your whole QMA hard problem in the precision of this matrix.
Okay. Oh, okay.
So it's actually really...
They actually take the limit n going to infinity. So the input is the number of bits of the...
The input is the number of bits in your matrix. That's where you encode your problem.
Okay, thank you.
Any other? Oh, sorry.
Hi, I was wondering, do you think that the techniques that you apply here could also generalize to 1D long-range systems?
If it's polynomially decaying, I'm not optimistic. If it's exponentially decaying, I think yes. We have actually, I've always advertised this work here, which is very old and hard to read. There's a nice newer version of this work, which is much better to read and which we actually cite all the time, which considers for this analyticity of free energy the case of exponentially decaying correlations. And they actually get that the statement of there are no phase transitions in 1D is actually maybe not true, because there might be they get the same result, but at only below a critical temperature. So there's another thing. There might be a critical temperature in 1D, and below the temperature it might fail, but apart from that, it should basically work the same, I guess.
Right. Okay. Thanks.
Okay, let's thank the speaker again.